So how is it possible that a soft, gray pencil lead and the hardest, most brilliant gem on Earth can be made of the exact same thing? We're talking about just carbon atoms. Today, we're going to unpack the incredible tale of diamond and graphite and see how their structure is literally their destiny. Let's break down how this all works.
I want you to think about it like this. Carbon atoms are like Lego bricks. If you have a pile of the exact same bricks, you could build a spaceship or you could build a house. They're totally different things, right? But they're made from the same fundamental blocks. In chemistry, it's not just about what atoms you have. It's all about how you connect them. And that is the core idea we're going to explore today.
And, there's a fantastic word for this whole phenomenon, allotrope. Diamond and graphite are both allotropes of carbon. They are both solid carbon, but the atoms are arranged in completely different ways, which, as you're about to see, gives them wildly different, even opposite, properties.
So here's our game plan. We'll start with what we're calling the allotrope puzzle. Then, we'll get up close with the rigid network of diamond and contrast that with the sliding layers of graphite. After that, we'll have a head-to-head clash of their properties. And finally, we'll take a quick look at silicon, which is kind of like electrons in its outer shell. We call these its valence electrons. And 4, well, that's the magic number. It means each carbon atom can form 4 really strong connections or covalent bonds with its neighbors. This high bonding potential is the secret sauce that allows it to build the huge diamond. Every single carbon atom is bonded to 4 other carbon atoms. This creates this incredibly strong, interlocking 3D network. We call it a tetrahedral lattice. It's like a continuous web of super strong bonds with absolutely no weak points.
And these structural facts, they have major consequences. This rigid network is exactly what makes diamond the hardest natural substance we know of. It also means that all 4 of carbon's outer electrons are locked up tight inside these bonds. There are no free electrons to move around, which makes diamond an electrical insulator. It just won't conduct electricity.
And to break the millions upon millions of these strong covalent bonds, well, you need a tremendous amount of energy. That's why diamond has an unbelievably high melting point. We're talking over 3,700 degrees Celsius. Instead of that 3D lattice, graphite forms these flat hexagonal sheets. And in these sheets, each carbon atom is only bonded to 3 other carbons. These layers get stacked on top of each other, but, and this is the crucial point, there are no strong covalent bonds holding the layers together. Instead, they're held by much, much weaker forces. You can almost think of them like sheets of paper just stacked on top of each other. So what does this all mean for its properties? Well, those weak forces between the layers mean they can slide past one another really easily. This is why graphite is soft and slippery. It's perfect for things like lubricants or pencil lead. When you write with a pencil, you're literally shearing off layers of graphite onto the paper. And hey, remember that 4th electron? Don't worry, we're going to come back to that. It's important. As simply as possible. Diamond is hard because its atoms are locked into that super rigid 3D lattice. It's perfect for cutting tools. Graphite is soft because its atoms are arranged in layers that can just slide around. It's perfect as a lubricant. It's the same atoms, but they have opposite properties, all because of their structure. Right, we said that in graphite, each carbon only bonds to 3 others, but carbon has 4 outer electrons. So what happens to that leftover electron? This is where the story gets really, really interesting.
So that spare electron, it isn't locked into a bond. It becomes delocalized, which is just a fancy way of saying it's free to move along the layers. Now remember, electricity is just the flow of charged particles. This diagram shows it perfectly. In diamond, the electrons are locked up tight, so it's an open circuit. No electricity flows. But in graphite, you have this sea of delocalized electrons that can carry a current, closing the circuit. It's a conductor.
So let's just recap the showdown. You've got a rigid 3D lattice versus flat sliding layers. You've got extremely hard versus soft and slippery. And you've got an electrical insulator versus a conductor. Really, the only property they share is that very high melting point. And that's because the covalent bonds within graphite's layers are still incredibly strong and take a lot of energy to break. Here is silicon dioxide, but you probably know it as silica. It's the main ingredient in sand and quartz. And what do you notice about its structure? It's a tetrahedral arrangement, just like diamond. You have silicon and oxygen atoms locked into a continuous, rigid 3D lattice.
And because it has a diamond-like structure, guess what?
it has diamond-like properties. It is very, very hard, it has a high melting point, and it doesn't conduct electricity because, you guessed it, there are no free electrons. This really proves the rule. A giant covalent lattice structure leads to these specific, predictable properties.
And believe it or not, carbon's story doesn't even end with diamond and graphite. There are other allotropes, like fullerenes that are shaped like soccer balls, and graphene, which are sheets that are only a single atom thick. Carbon's ability to connect in all these different ways truly makes it one of the most versatile and important elements we have.